related to organic solar cells, which is the structural properties relationships study from the molecular design to the new application of organic solar cell. So today I will focus on mainly two topics. One is the structural properties relationship related to the efficiency of organic solar cell. I will talk about the crystal structure of organic semiconductor, their charge generation properties, and their relationship with the performance of OPV. I will also talk about the device architecture of organic solar cell and their optoelectronic properties, which lead to the very important application of solar cell, which is the semi-transparent solar cell application. So let's take a look at the background, right? It's about 35 years ago, right, for the first demonstration of organic solar cell. At that time, Professor Qing Tan, who is also the inventor for OLED, at that time they tried to make a bilayer organic solar cell based on this donor type and also acceptor type material, forming this PN junction similar to inorganic solar cell. And then he successfully get performance up to 1%. And about 10 years later, Professor Alan Heger and also Dr. Yu Gong, they start to use another process, which is solution-based process, by mixing polymer and solution processable fullerene derivative to make so-called the bulk heterojunction. And this also demonstrate the possibility to make solution processable organic solar cell. And at that time, both of these type of device give a 1% efficiency. So nowadays, after 20 to 30 years of development, there are huge progress on the improving the performance of organic solar cell. Nowadays, the single junction or tandem solar cell already show up to 18%, making them more and more competitive. And even in module, they are also showing over 10%. And several companies also focus on the manufacturing of organic solar cell, and they have demonstrated that these organic to roll coating process, either solution or vacuum deposit process, also can demonstrate a solar cell with flexible, very nice looking, and look very different from the inorganic solar cell. So this is a tremendous benefit, right, with the increase of the performance over the few years. Last few years, it really make it more close to market ready. So of course, right, for organic solar cell, we are not targeting to compete with the silicon solar cell right now, but it do have some very unique features. For example, they are flexible, they are non-toxic, and very beautiful. And depending on their performance, we can use it as a wearable or portable power source, or more interestingly, because they can make into semi-transparent solar cell, we can also using them as a potential power generating window. If their performance can be compatible with perovskite or a silicon solar cell, it may even be used for grid connected PV, large power generation. So far, these are the new market for organic solar cell, flexible organic solar cell. And of course, the key scientific problem for organic solar cell is organic material. They are usually has a low dielectric constant, which means the exciton binding energy, right, in organic material is large. We need to use extra energy to overcome this exciton binding energy in order to separate the hole and electron once they create an exciton. That actually lead to more energy loss due to this photocurrent generation process. So there are lots of effort trying to understand, right, and correlate from the material point of view, right, how we can reduce the loss in organic solar cell. Previously, when we use a fullerene as the acceptor material, we do see a quite large energy loss, right, during the charge generation process. But recently, we have some new development on the non-Fullerene acceptor, allow us to further reduce this loss. This is also the origin of the increase of the performance in the past couple years. So if you look at this NREL champion efficiency chart of different type of solar cell, the one with this orange circle are corresponding to the organic solar cell. You can see at the early development, we are focusing on controlling the nanophase segregation morphology that required to efficiently generate the charges, right? And later on, we have a more and more new material developed that has a better absorption, better energy level, create larger VOC, and also with better charge transporting properties. So in the year between 2005 and 2015, the performance of organic solar cell continues to improve because of the development of new donor. And in the past couple years, there are new non-Fullerene acceptor developed and then allow the performance to continue to increase. But the really big increase of the performance is a new generation of acceptor material developed about 2 years ago, which allowed the performance of OPV increase from about 12% to up to 16%. Okay, so we are involved in that development with our collaborator in Central Southern University. So we luckily can make a mark on this NREL chart. Okay, and of course this is about 2 years ago, and nowadays the performance of organic solar cell further improved up to 18%. And based on a similar type of derivative of the non-Fullerene acceptor material. And in City University of Hong Kong, we do have a performance now close to 19 or 20%. So this is a very exciting time for organic solar cell development. And of course, we are trying to understand why this new type of non-Fullerene acceptor, which has a band structure, we call it, this is electron accepting group, electron donating group, and at the middle also has an electron accepting group. So this forms so-called the ADADA curve type structure. So this is a very low bandgap material with absorption up to 950 nanometer. But compared to the previous champion non-Fullerene acceptor, we found that although, right, it absorbs more light, generate more photocurrent, the VOC, right, the open circuit voltage doesn't really drop, and it has a very good EQE. That means the overall energy loss in this material is small while maintaining a very good photocurrent generation. This is the reason why it gives a very good performance. Okay, and of course, to really understand, right, why it gives us such a good performance, we really need to take this structure performance relationship study, learn from traditional material science into this organic solar cell area. So we are trying to understand the chemical structure of the molecule and trying to understand their crystal packing. And then because we have donor acceptor material, we also need to know its nanophase separation morphology. And this, all of them will affect the charge dynamics, charge separation process in the bulk junction. And eventually, we also need to take care of the charge extraction in the device. So this completes the whole study for the structure performance relationship for organic solar cell. So now we are trying to take a look at the molecular packing of this new type of molecule. And about 2 years ago, we actually successfully grow a crystal out of this Y6 molecule. And then this crystal structure actually composed of 4 layers of the molecule. And you can see here is the first layer of the molecule, all of this Y6 molecule pointing in one way. And if you look at the upper layer, the second layer, you can see they are now connected to each other, forming this U-shaped dimer with the acceptor stacking on the bottom layer acceptor. And the third layer, they further have connecting this dimer, right, into this direction pointing in this orthogonal direction, and the fourth layer actually complete the crystal structure. So now this two-dimensional, three-dimensional packing network is very rare in organic semiconductor. We very seldom can see such an interesting structure. And if you do a further analysis of that, you can see the acceptor here, which corresponding for electron transport actually is a stacking on this field channel. And then this blue region consists of the core, fuse core, and acceptor stacking, and also core to core stacking. And then the hole here actually is corresponding to all the side chain. So with this crystal structure, we will be able to further analyze the charge transporting properties by using this DFT calculation. And you can see from the left part, which is the delocalization of the holes, the HOMO delocalization, you can see they are more in the lateral and also vertical direction. The holes can be delocalized in that direction due to the core and core stacking. And for the electron, the LUMO level actually is in the vertical direction. So this is very interesting because from the calculation, we find that both electron and hole actually can be delocalized in the crystal, making it as an bipolar charge transporting material. And of course, based on this analysis, we can also check out the exciton coupling, which has a pretty large value, right, for this Y6 material by itself. And we can translate this coupling, exciton coupling, to the Hoping wedge, which is in the sub-picosecond level. That means the exciton diffuse very fast. The good thing is, if the exciton diffuse very fast, we will be able to reduce the coupling to the vibration of the molecule. This is very important for improving the exciton lifetime and also reduce the long radiative loss. So from the time resolved PL, we find that this Y6 do have a longer lifetime. It has a longer exciton lifetime, and it also have a larger PL quantum yield compared to other acceptor, which is why this is because, right, the reduced long radiative loss, which explain the overall energy loss is small during the photocurrent generation. And of course, the previous just show you that this is a crystal structure, not necessarily mean when it is deposited into a thin film, they still maintain the structure. So therefore, analyzing the morphology and the crystal packing in the thin film is also very important. Therefore, we do a GIWAXS study with a pure Y6 thin film. And then you can find that from the GIWAXS study, the out of plane peak actually contain two peaks, which correspond very well with the packing of the crystal structure we observe. And then for the in-plane GIWAXS peak, we also can find the corresponding distance or the lattice distance associated to the packing of the crystal. That means the crystal packing preserved very well in the pure film, okay? And then they have the face-on orientation, the face-on packing parallel to the surface, which is good because now the charge transport is vertical to the surface, which is very important for taking out the hole and electrons into the corresponding electrode. And this packing also preserved when we mix this Y6 acceptor molecule with the polymer donor. Okay, so this is now we can conclude that actually the very interesting charge transporting properties should be preserved in the real device. And of course, based on molecular dynamic simulation, we also can study the packing of the Y6 molecule. And we do a lot of simulation and find out that the packing mode actually mimic very well with the single crystal structure packing mode with all these dimer pair, 3 different pair, actually we can all find it in the single crystal. And even for the blend film with the polymer, we also observe similar dimer structure, okay? That allow us, right, to further analyze the exciton binding energy within this brand film. So we take out the optimized packing, right, from the molecular dynamic simulation. Find out that if we only have one acceptor, and then when it is close to the polymer, right, when the light shine, right, on this material and it generate the exciton, right, the electron and hole distance actually is about 2 nanometer. However, if now, right, the Y6 molecule pack very well, forming some aggregate at the interface. For example, now when we extract 3 molecules packed together, then the electron and hole pair distance actually extend to 5 nanometer. That is very important because now, right, once this exciton binding, the hole and electron become separate larger, then it's easier to dissociate this hole and electron. So we find that, right, from this monomer to this trimer, the Coulombic attraction at this donor acceptor interface actually reduced from 160 to 70 mini-eV. And in the real case, we are expecting the hole and electron actually will further delocalize, and then the exciton binding energy should be smaller, maybe close to the room temperature, which is 25 mini-eV. Okay, so this is good, right? Now we understand this very good packing of the non-Fullerene acceptor, and also their very nice exciton and also charge transport properties allow us to very efficiently dissociate the charges. So this actually helps us to have some guideline to design new generation of a molecule. So with a very quick summary, we find that the formation of the delocalized and emissive exciton enable a very small long-radiative voltage loss in this stage of art materials for OPV, and also the delocalization of electron and wave function at the donor acceptor interface significantly reduce the Coulombic attraction between the interfacial electron and hole pairs. And the CT states are also significantly weaker, right? This non-radiative decay pathway are required in new generation OPV material to further reduce the VOC loss. Okay, so this is the first part about crystal structure and performance relationship in OPV. So with a few more minutes, I would like to share with you the other area we are working on, which is the optical management for OPV. And as I mentioned, right, the semi-transparent properties is very important for this OPV new application, and it requires us to understand better about the optical properties in organic solar cell. So we adopt this so-called the transfer matrix model, which is based on the when light traveling from one media to the other media, right? It will either get reflected, absorbed, or transmit. When we build up this transfer matrix model, we will be able to analyze the electromagnetic field or the optical field within multi-layer structure. So this is very important to understand the optical properties of organic solar cell. So with this transfer matrix model, we need to know the reflective index and also absorption coefficients for all the layer we use in the organic solar cell. Then we apply into this model, and then we will be able to analyze the electromagnetic field and the exciton generation profile within the active layer, and also do the optical loss analysis for the whole device. We can even analyze the color properties of the device. The first application actually we use is for the tandem cell, because in the tandem cell we use the front cell and back cell to absorb different portion of the light. For example, visible and also near IR light, right? And we need to balance the light absorption properties because they are connected in series. So that actually complicated the design of the tandem solar cell. Therefore, we can use this transfer matrix model to estimate the best device architecture that can give us the right thickness for each layer and give us the big biggest photocurrent out of that. With that, we continue to improve the performance and then also lead to a very high performance device for the tandem cell in over 17%. And of course, as I mentioned, the semi-transparent properties is very unique for organic material, although in inorganic solar cell, they can also make them into semi-transparent. For example, amorphous silicon, if they are very thin, they can also be semi-transparent. But the intrinsic optical properties for organic material is we can tailor their absorption. You can imagine that if we can design some organic material with absorption mainly in the near IR, then we will be able to allow more light to transmit in the visible range, which is perfect for the window application. We introduce a concept so-called the optical genome engineering. So what we are doing here is trying to build a materials database, which is mainly the optical parameters of different material used in the organic solar cell. And then we also improve the transfer matrix model by increasing the calculation speed by close to 10,000 times for the compared to the commercial one. With these two, right, database and also high throughput model, we will be able to, based on whatever we input right into our computer. For example, in the tandem cell or semi-transparent solar cell, when we want them to have a different optical properties, we will be able to ask our computer to select the right material and then the right device architecture so that we can reduce the time right on the experiment, but getting the best out of this semi-transparent solar cell. So here I would like to show you one example. In the bottom part, actually, for the organic solar cell, we have the ITO as the transparent electrode, and on the top electrode, we also can introduce a very thin transparent silver film as the electrode. This is the basic of our organic solar cell. But at the same time, right, we can also introduce a distributed back reflector, which composed of alternating layer with different reflective index. The good thing is now, right, we can control this stop band so that we can allow, for example, the near IR light reflected back to the cell, but then we can allow the visible light to pass through it so that we can increase the overall light absorption of the bulk junction, right, in the organic solar cell. However, for the stop band equation, right, it usually gives you a very sharp edge. If you look at the transparency associated to window, we are talking about our sensitivity of eye, which do have a shape, right, localized in this green region, 550. So now if we want to design the photonic crystal that is maximize this transmittance, we don't have an equation that can help us to do that. Therefore, with this high throughput analysis, we will be able to allow all the layers to change their thickness simultaneously, okay, in order to find out the matrix of that. So therefore, with this high throughput modeling, we are calculating all the different combination of the device, giving out the performance and also the transmittance relationship. We calculate more than 40 million of device in 1 hour, okay? So it gives you the curve, right? Whatever on this curve, you will give the best combination, right, of the efficiency and also transmittance. So we, based on this calculation, we pick up a few points to verify our result, right? So this is the configuration of this special designed distributed black reflector. And just based on this modeling guided device structure, we will be able to get the performance actually matching very well with the modeling result, okay? So we will be able to very easily to get high performance, but also with desired optical properties. So this is the beauty of this high throughput optical engineering model. And here I show you another example. We can even ask the computer to design the structure that gives us a very good color rendering index, okay? performance, transmittance, color rendering index with the function of the different layer. Okay, and then this is the generated simulated result. You can see the red, green, and also blue peak having a very neutral color, and this is the experimental result matching very well with the simulation, and then we are getting very high performance out of that. So anyway, I would like to summarize in 2 slides, and with this high throughput optical engineering or optical genome engineering, we will be able to selectively actually guide us to make a very good semi-transparent solar cell with tailored optical properties. And if you look at the performance of the inorganic solar semi-transparent solar cell right now, it's about 5% efficiency and 20% visible transmittance. But organic solar cell already surpassed this performance a lot. And further using this optical guided design, we will be able to make organic solar cell actually is 2 times to 3 times better than the best inorganic transparent solar cell. So we will be able to also explore the application for rollable solar curtain, or we use it as a BIPV together with this heat insulation or heat isolation function, using it on electrical car, or even can tailor their spectrum for greenhouse application. With that, I would like to conclude my, make a conclusion, and, and of course, right, for the organic solar cell over the past 2 years, we see excellent improvement on the performance. And I think with our recent demonstration of a very good stability up to 15 to 20 years, we will be able to really explore this new type of solar cell technology for many different applications. And with that, I would like to thank my group and also our funding source. And I would like to also thank you for your attention.